Hey there, team. All right, continuation of the last video. We covered atomic line spectra and how Niels Bohr, with his Bohr model, kind of explained that, borrowing quantum ideas from Max Planck and we integrated that in with Planck's equation for energy and photons, brought to you by Albert Einstein. That video would have went way too long if we did some mathematical calculation. So I just like to cover what the concept was that classical theory had a hard time explaining, who brought quantum ideas in and explained it, qualitatively or quantitatively if I had time. But we didn't have time to quantitatively do it. So let's do electron transition calculations today. Ha ha ha. Like I said, the meat and potatoes of this particular chapter. I love being able to take the theory, the quantum ideas of Bohr with the resulting Bohr's equation from that, and several things we can do for it. My particular favorite is to give you an initial and a final quantum level or orbit, right? So say an electron's in orbit 7 and drops to orbit 4, starts in orbit 3 and relaxes to orbit 1, or starts in orbit 1, gets excited to orbit 4. Whatever it was, just figure out whether you're absorbing or causing excitation or emitting radiation due to relaxation. What's your initial n value, principal quantum number, or electron orbit, and what's your final? Well, Rydberg constant's a constant I provide you, right? And you can solve for the change in the energy that's going on. And that's for hydrogen. If you have a hydrogen-like species, right? So we've got cations with one electron only. So however many protons they have, you just remove enough electrons so you have one left, right? Helium plus 1, lithium plus 2, etc., etc. You just adjust. I gave you the equation for the energy in the last video, but if you rederive Bohr's equation for this, you get exactly the same thing. It's just modified with the number of protons in the nuclear charge. So just take the nuclear charge or atomic number times, square it. You're good to go. This is a much oversimplified version, right? We found out it worked for hydrogen, but not really well for anything else. We need to get to the wave mechanical model later. So after we do some calculations, we'll do a couple of videos for some new ideas that were proposed or discovered after Bohr did this. Right? Bohr didn't have those arrows in his quiver, so he had to kind of morph here's quantum theory and here's classical theory. He kind of bridged that divide. It wasn't all classical, it wasn't all quantum, but he was the first one to step through the gap and say, come on, people, let's go. And then a lot of other people charged through that gap after, but he just didn't have the information some of the people did 10, 15 years later to develop a more sophisticated model. So we just got to modify it with that. But you try to apply this to uranium or something, anything with multiple electrons, it gets pretty crazy. And then remember the qualification here. Because of the quantum transition, electron can go from one orbit to another, not in between, right? So the photon energy has to match exactly the energy difference between those two particular electron energy levels. It can't be, you can't promote it from n equals 1 to 3.2 because the photon energy was too high. It's very specific wavelengths it's going to absorb, or if it drops down, re-emit, and that gives you the atomic line spectrum. And remember to take the absolute value, because if you're relaxing, going from a higher energy to a lower energy, that atom is losing energy, so delta E will be negative, and we have to make it positive to get a positive photon value. Otherwise, you end up with like a negative wavelength or something. And you can calculate frequencies from Planck's equation, or you can calculate wavelengths, depending which one you're after. Usually I'm after wavelength, and I love having you calculate the wavelength that's emitted or absorbed, and then tell me what regions that's from. I gave you the wavelength ranges, right? You could tell me if it's from the visible region and technically what color, or get pretty close. Is it infrared, right? We talked about near infrared, far infrared. If it's UV, you could even do UVA, B, or C. Is it in the microwave region, X-ray region? You could do all this fun stuff. Or vice versa. I could give you a color if it's visible, or a wavelength. You could calculate the energy of the photon, relate that to the energy difference between the transitions, and if I give you the initial n, you can calculate where it's promoted to or relaxed to, or if I give you the final n, you can tell me where that electron originated from. Oh, because that's it. Either you're solving for that or that. And I love the connection. Meat and potatoes. Let's do a couple examples. Let's do one where we're solving for an n value. I think those are a little more challenging mathematically. And another one where we're going to solve for a wavelength and color, and we'll talk about different kinds of transitions and how they corresponded to certain people who discovered those types of transitions, and they have special names. Get your calculators ready. Here is a very typical problem you may run into in a quiz or exam in my class. One of two, right? There's two ways you can work it. Start with the wavelength or color, figure out an n level, or start with the n levels, figure out the energy to get to a wavelength or a frequency. All right, so here we've got an electron in the n equals 2 orbit for hydrogen. Always assume it's hydrogen unless otherwise specified, because that's pretty much all it really works for a while. So we've got an electron in the n equals 2 orbit. Of hydrogen, I don't necessarily need to state that, absorbs violetish, is that a word? It is now violetish light of 434.1 nanometers. And you'll see from one of the prior videos when we looked at the 4 lines of the atomic line spectra of hydrogen, that was one of them. That spit out. What orbit is that electron promoted to? Boop! Now I could have flipped this and say, hey, it started here and relaxed to n equals 2. Same thing. So how are we going to approach this? Well, remember 2 steps. Let's do this. So step 1, here's how you think about these types of problems. Once you know how to do it, they're pretty easy. So step 1, let's see, I know the initial n, I know the wavelength, I'm solving for the final n value, right? So promoted to would be NF. Identify what you're solving for. Are you solving for a wavelength? Are you solving for a quantum number? What are you solving for? Which means I need to take this wavelength and solve for the photon energy, which should be equal to the energy change between the 2 quantum levels, right? That delta E. So what we're going to do is solve for the energy of the photon, right, using Planck's equation. Easy enough, right? Nothing we haven't done before. Let's look at step 2. Once we have that, now some people skip step 2. It seems automatic. We need delta E. And remember, E photon, because the quantum transition is equal to the absolute value of that. All right, and then step 3, and a lot of people just do step 2 in their head. You don't have to show me that one. So step 3, once we have delta E, we're going to solve for n final using Bohr's equation. There you go. And then the next sample, we'll do 2 examples. Next one, we'll just reverse it. We'll use Bohr's equation, equate it, and off you go. There's one little trick here with the energy levels that you may run into. We'll deal with it when we have it. So go ahead and calculate it if you're feeling adventurous. Let's go ahead and do step 1, and then 2, and then 3. We probably have to do separate boards for those. Let's do 1 and 2 on the next board. Step 2 might seem a little redundant here, but anyway. Now, we've done step 1 before, right? We did that, I think we were under the photoelectric effect video. So here's the energy of the photon using Planck's equation. It's Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. Either one. I tend to like to work with wavelengths, not frequencies. Just me. So let's put in Planck's constant, which I would provide for you, 6.62607 times 10 to the minus 34th joules times seconds. You could put per photon here if you wanted to, but really we only do that, it's implied, we only do that if we want to get to kilojoules per mole of photon. Divide by the wavelength, 434.1 nanometers, and multiply by the speed of light, which I would provide for you, 2.997925 times 10 to the 8th meters per second. Notice meters don't cancel nanometers, so you got to have those units in there. So seconds cancel seconds, convert nanometers to meters, so a billion nanometers per meter. Nanometers on top, nanometers on bottom, meters on top, meters on bottom. Leaves it with joules, technically joules per photon. Remember, photons have real tiny numbers, and if you want to convert that to kilojoules per mole, it gives you a more decent number, but we don't need to. So I get 4 sig figs from the wavelength, 4.57601 times 10 to the minus 19th joules, with a vertical dash line after the 6 to go 4 sig figs. So that is the energy of the photon based on the wavelength that was provided. Okay, well, that's the photon being absorbed. right? Transferring momentum of the electron. Boop, electron pops up to a higher orbit. So it started at 2. Where's it going? Oh, we would like to know that. That's what we're going to answer in step 3. So step 2, you could just do that in your head. Obviously, for an excitation, absorption, the atom is gaining energy. The photon is transferring energy. It's a transfer. Electromagnetic radiation is an energy transfer process. So the energy is going up, so it should be a positive value. For relaxation, it'd be negative. So we don't really need to worry about this. We don't need to take the absolute value. Obviously, the energy of the transition from 2 to wherever we're going is going to be the same number, 4.57601 times 10 to the minus 19th joules. Now in step 3, let's take that delta E, plug it into Bohr's equation, plug in the initial value of the n I gave it, n equals 2. Where does it go to? Ooh. Now, obviously, if we get an answer that's not an integer, either that transition's not allowed or we screwed up our math. One of those two. So we should get an integer within, 3, 4, 5 decimal places. Here we go. Let's do step 3. I agree. The math sucks on these kind of calculations. Solving for n initial or n final is not pleasant. It's not hard, but I find a lot of students, they get the chemistry right and just screw up the math at the end, right? Solving for wavelengths and energies, that's pretty easy. It's the n, because if you're solving for n final, it's in the denominator, you're subtracting it, so you gotta inverse crud and move negative signs around and take square roots. This took me like 1, 2, 3, 4, 5, like 7 or 8 steps. Blah. I ran out of space on my board, so follow along with me. So here's Bohr's equation. I know delta E from earlier. I know the Rydberg constant. I'd give that to you. I know the initial n. I'm solving for this. Yuck. All right. So all I did is move the Rydberg constant down, put those two parameters together. So that'll equal 1 over n initial squared minus 1 over n final squared. So I'm going to try to get that term. So there was my energy from before, 4.57601 times 10 to the minus 19th joules, good to 4 sig figs. Rydberg constant, R sub h, 2.179 times 10 to the minus 18th joules. I would provide you that. Equals 1 over 2 squared, or 1 over 4, which would be, 0.25, minus 1 over n final squared. So if we take the delta E divided by RH to 4 sig figs, I get 0.210005. That should equal 1 over 2 squared, which is 0.25, minus 1 over n final squared. So I've kind of simplified things. All the units went bye-bye. So obviously I need to pull this to the other side. So to isolate here, to isolate the 1 over nf squared, I got to take the 0.210005 minus 0.25. So I'm moving the 0.25 to the other side. And then I move the negative sign over as well. So 1 over n final squared will be 0.210025, good to 4 sig figs, minus 0.25. And then I'll take that term and make it negative. Because obviously that's a smaller number minus a bigger number. That's going to give me a negative value here. And the negative signs cancel out. You can't end up with a negative n value. It makes no sense. How could you have n final of negative 4? What does that mean? It's inside the nucleus? So when you do the subtraction, the 0.25 is exact. Quantum numbers are exact. So we're limited to 4 decimal places. So I get 0.039995. That's that whole term. So 1 over nf squared is 0.039995. Well, I need to isolate nf squared, so I need to take the inverse of both sides. So nf squared will just be the inverse of this, or 1 over 0.039995. This is where a lot of students screw up, right here. I'm just warning you. Might look easy to you, but when you're on your own, you're like, blah, what just happened to my math? And then since that's squared, I need to take the square root of 1 over 0.039995. And when I do that, I get 5.0002. Good to 3 significant figures, because when you go to 4 decimal places, you end up with 3 significant digits. Obviously, that looks pretty close to 5 to me, so you just round that to the nearest integer. So n final is 5. So let's show that transition real quick. Let's do what's called a Bohr diagram, or an energy diagram, and show you that transition real quick. 2 ways you could do these Bohr diagrams: the big bulky way and the simplified way. I don't care. You can, pick your poison, whatever you want. So if you want to follow the pure Bohr model, the planetary model, you got the nucleus in the center, n equals 1, n equals 2, 3, 4, 5, all the way to infinity. You can draw those circles. Now, imagine those are perfect circles. The engineer in you is crying and vomiting, and you're getting things in your throat that burn with stomach acid. That's all right. Not my favorite. I like the shortcut method. So if we did it here, let's say our electrons in green, we're starting at n equals 2, right? And we're going to n equals 5. Boop. That's our final. And what's happening is because we've got this violet photon coming in. So here's our photon, moving with incredible wave-like motion. I don't know how to draw that. So boom, transports the energy, bam, pops up to n equals 5. So that's an excitation, right, due to absorption of energy. Now, if you don't want to draw those stupid circles, you can just represent it with a Bohr energy diagram like this. Just say, hey, here's our energy. Here's n equals 1, n equals 2, 3, 4, 5. And it turns out when we look in more detail later, they actually get closer and closer together all the way up to infinity. It just looks like a giant black line. They're so close to each other. So the gaps get smaller and smaller and smaller. That's going to create some serious issues towards the end of this when we get to the wave mechanical model. So in this case, we're starting at n equals 2. That's our electron. And it shoots up, boop, to n equals 5. So that shows that transition there. And that obviously was in the visible region. So this n equals 2, we're going to find out is for the hydrogen, happens to be where if an electron starts at n equals 2 and moves up, it absorbs visible radiation. If it starts higher and ends up in n equals 2, that gives off visible radiation, some color. That was the first one to see that Balmer saw. So we're gonna that ends up being called the Balmer series. I'll summarize that in another video. I'll do the 3 different ones. So we're going to be looking at the magic ones where 3, 2, and 1. We're going to find out create these different kinds of series. So 2 just happens to fall in the visible region. That's the Balmer series. I'll do an overall summary later for you. All right, so one type of calculation, that was the tough one. Let's do the easier one now, where instead of solving for n, I give you n initial, n final, we'll solve for the wavelength. Get your calculators out for another round. It hurts. Problem number 2, another one you will likely, big hint, capital H, probably see on a quiz or exam. It'll be either this one or the other one. Either you're solving for n or solving for a wavelength. So we've got relaxation, so it's starting high, going low, which means the atom's going to lose energy and delta E will be negative. Hey! Relaxation of electron and hydrogen. And again, if I didn't say that, we would assume it was hydrogen. Always assume hydrogen or a hydrogen-like species if I specify it, but we're not going to do any multi-electron species here. Starting with n equals 7, going down to n equals 1. You could also draw a Bohr diagram, an energy diagram. Please, would be nice. And since you know the n values, you could actually do that before you do the calculation or after, doesn't matter. That causes emission, obviously. If an electron drops down and relaxes, that energy difference gets spit out as a photon. What wavelength was that photon, right, in nanometers? And what region of the electromagnetic spectrum is that from? Is that microwave? Is it radio, X-ray, ultraviolet, infrared, visible? And if it is visible, try to estimate the specific color. Is it orange-ish? Blue-ish, indigo-ish, violetish-ish. Have at it, right? So again, steps are just the opposite of what we did before. So step 1 in this case, we know the n's. We're going to calculate delta E using Bohr's equation. That should be easy. Right? And I'll provide you the Rydberg constant. Step 2, again, we're equating, remember, E photon. Oh, I spelled photon wrong. And that delta E could be positive or negative. Positive if it's going lower to higher n values for absorption. Negative if it goes higher to lower and relaxing, right? Is the atom gaining energy or is it losing energy? So if it's negative, just make it positive. You could do that in your head, right? And then step 3, we can use Planck's equation. We're going to solve for the wavelength using Planck's equation. Thank you, Einstein. Einstein! There you go. Again, if you're feeling daring and adventurous, plug your nose and jump off the cliff into the ocean below. Poof! See if you can get it before I do. Track your uncertainty. Let's do it. All I could fit was steps 1 and 2 on the board. All right, there's Bohr's equation there. Rydberg constant, 2.179 times 10 to the minus 18th joules, always given to you. N initial is 7, so 1 over 7 squared, minus 1 over N final. Now, N final's 1. Oh, so that'll be 1 over 49, minus 1 over 1 is 1. So 1 over 49 minus 1. Now, remember, these are exact, so there's no limitation on sig figs there. So let's do that term. So delta E will be the Rydberg constant times negative 0.9795918. You can do as many digits as you want to because that's considered exact. So we'll be limited to the 4 sig figs for the Rydberg constant there. And that should be a negative value because we're relaxing. The atom's losing energy. So you're taking a smaller number minus a larger number. Don't forget the negative sign or you're in trouble. So delta E, if we take the Rydberg constant times this term, I get negative 2.13453 times 10 to the minus 18th joules. Good to 4 sig figs, and that's right around the range of photons. Individual photons are right in the 10 to the minus 18th, 10 to the minus 19th range typically. Maybe shoots to 10 to the minus 20th. Now step 2, we want the energy of the photon. That's the energy of the electron transition from 7 to 1. Boop! That quantum mechanically, that's exactly the same energy the photon released. Pow! And so, since that's negative, obviously we're going to have to take the absolute value of that. So the energy of the photon is the absolute value of the energy transition. So the absolute value of that will, of course, be 2.13453 times 10 to the minus 18th joules. Carry the non-significant or intermediate value through. And again, step 2, you can do that in your head. You can just state it and write it down there or whatever you want. It should be pretty obvious. Now let's do the last one. Use Planck's equation. You now know the energy of the photon. You know Planck's constant. You know the speed of light. Solve for the wavelength. Convert that to nanometers and tell me what region of the electromagnetic spectrum that is. Good luck on your journey and your mission. Did you get what I got? Here's Planck's equation. So energy is hc over lambda if you're dealing with wavelength. We're not dealing with frequency. Some people like to use the speed of light as the frequency times the wavelength, solve for the frequency first, and then use E equals Planck's constant times frequency, and do that in 2 steps. That's fine. I just like to do it all in one. I just do the substitution and I'm off to the races. So Planck's constant, 6.62607 times 10 to the minus 34th joules times seconds, technically per photon. You got that memorized yet? Divided by the energy that we got from the earlier step. That's a 2.13453 times 10 to the minus 18th joules, good to 4 sig figs. Multiply by the speed of light, 2.997925 times 10 to the 8th meters per second. Get that memorized? 2.997925, 2.997925, 2.997925. I'll give that to you though. We wanted that in nanometers, so I got to convert meters to nanometers. 1 times 10 to the 9th in nanometers are 1 billion nanometers per meter. Meters cancel. Seconds cancel, joules cancel, leaving me with, yay, nanometers. And that really helps us in the visible ultraviolet range and even in the infrared range, which can run into the micrometers or microns. Anyway, to 4 sig figs, I get 93.0624 nanometers. That does not round up, so it stays as 93.06 nanometers. Now remember, we want the region, so the visible region, I want you to remember, is about 400 nanometers in violet to about 750. Some people go 750, 800 in the reddish range, right? So it's obviously a lower wavelength than 400s, and lower wavelength is higher energy. So this must be the region to just 1 over below the violet. Below violet. Ultraviolet, yay! And if you want to be a fancy pants, you can look at my video on the electromagnetic spectrum and go, was that UVA, B, or C? UVA is the lowest energy, which is butting up right against the 400 nanometers. UVB is right in there. And so this would probably fall more in the UVC, more of the higher energy. I think UV goes about 400 to about 10 nanometers, maybe 1 nanometer, somewhere in that range. So that's approximately the UVC region. If you want to be super specific. So the only one where if you want to break up the region into something specific within that region would be the visible region. So if this had fallen between 400 and 750, I'd say, well, what color would you estimate that to be? Now do me a favor, draw the Bohr energy diagram. And you can do all the circles if you're a great artist like one of my daughters. Actually, most of my kids draw pretty well, way better than I do. Or you can just do the simplified version where you just draw the horizontal lines and show this 7-to-1 transition for me. Go! All right, here's my pathetic looking Bohr diagram. I didn't want to do the circles anymore. So here's it. Remember, there's no n equals 0. You can't be in the nucleus. So n equals 1 to 7. They technically get closer and closer the higher you go. So in this case, we're starting at n equals 7 and we're relaxing. Now, a lot of times when you see absorption or excitation, they use a straight line. And a lot of times with relaxation, you'll see a wavy line. Not necessary. You can use straight lines, whatever. So this is relaxation. And of course, that's going to emit a photon. So that emits a photon. You don't have to draw that, right? You don't need to draw the photon leaving. I just kind of like to just show, hey, it's relaxing, so it's releasing energy, going from higher energy to lower energy. This atom's reducing in energy, negative delta E. That's that delta E spit off as a photon of energy. That's that energy transfer. And if you're going up from absorption, that photon's coming in, right? Welcome to the quantum transition. All right, now there's a special name for that because that fell in the UV region. It turns out if you're relaxing any one of these, do it for 6, 5, 4, 3, down to 1, you're going to get values that always fall in the ultraviolet region. And that was discovered by Lyman. So that's called the Lyman series. Anything that ends in n equals 1 is called the Lyman series. And we saw things that n equals 2 happen to be in the visible region. It's a little less energy. Right? So, and that was the Balmer series. So what I want to do is draw a big one that goes all the way across the board and show transitions that end at 1, end at 2, end at 3, and show you roughly what energies they would be at, and the experimentalist who discovered those and those transitions are named after, and we'll be done with this video. All right, this just kind of summarizes different types of transitions you may run into. So here's a generic Bohr energy diagram. You know, I could go all the way up to infinity. And remember, infinity, if you go from an electron to infinity, it went bye-bye. You just pop that electron off and you ionize the atom. You now got a cation, right? So you can calculate ionization energies. Just plug in n final equals infinity, and you'll see 1 over infinity squared would be 0. So pretty easy to calculate ionization energies to form a cation, right? But we found in our first two examples, so the first one we started with 2 and went up, and it took a visible light. So if you start in 2 and move up or end in 2, that typically falls in the energy range. The delta E range tends to fall in the visible region. So you get the different colors in there. So anything that ends in NF equals 2 for a relaxation falls in the visible region. Or if you're exciting up to some, respectable, not up to like n equals 942 or something weird like that. And that was discovered by Balmer, and he was the one who first tried to, create an empirical equation for these transitions without having any quantum theory behind him. He just kind of forced it to fit the data because he could see those colors. All right, so it's named after Balmer. And the other example we did was 7 to 1, right? Remember that fell in the UV region? So anytime you're starting at a higher n, nothing weird, drops down to n equals 1, that's higher energy. Do you see the bigger delta E here than here? So higher energy than visible would be ultraviolet. And so that was discovered by Lyman. So it's called the Lyman series. And F equals 1. Anything that ends in n equals 1. Or vice versa, if you go from 1 up or something to a respectable n value, that'll give you something in the ultraviolet region. And if you drop to n equals 3, right, that's even small. That's smaller energy now, right? So biggest energy, ultraviolet, visible. What's one just underneath the lower energy than visible? Infrared, right on. So if you drop down and end in n equals 3, that puts you in a lower energy region or infrared. Of course, we can't see ultraviolet or infrared. And that's called the Passion series. Not like passion fruit, the Passion series, Paschen. Or if you go from 3 to 4, 3 to 5, that kind of stuff. There you go. There's your different regions. You can now do any kind of electron transition calculation. You are good for the exam. Right on.